Carlo, and thank you all for joining today. Let me start with a flashback of 8 years, because I'm at KTH, but I passed through the Netherlands throughout my academic career, and although I was never affiliated with Delft, I spent some time here, because my advisor, Sergio, here in the first row, was here in Delft, and this is taken from the archives. It's 8 years ago, or less wrinkles and younger and more hair. Okay, so it's great to be back here, and it's I had great memories here, and I'm very happy to be able to be here and tell you more about my research. Before getting into business, let me throw some advertisements and a few acknowledgements. I'm at KTH, as Carlo mentioned. We launched our group. We're a small group, and we work on the intersection of automatic control, optimization, and game theory. But we're expanding rapidly, so if you're interested in these themes and you're looking for the next step, get in touch and maybe explore our research through that keyword. Okay, but good research takes time, and we're a relatively young group, a little bit more than a year. So today I'm going to tell you some of my older research in collaboration with many people that are at ETH in Zurich, and some of them are in other places, and you may recognize a few faces over there. Marta, among them, that now is here as assistant professor. Okay, so it's about feedback optimization. You may have heard this keyword and this buzzword before, but I want to start with, rather than a very dry theoretical introduction of that, I want to give you an introduction that starts from the application perspective. And for doing that, I want to use this quote from Professor Peter Dankwerts, who was a famous chemical engineer at the University of Oxford, about the difference between scientists and engineers. He says, scientists solves the problems they can, and an engineer solves the problem he must. So the problem that we really must solve is congestion in transmission grid. In this map that you see here, this is a part of France, the local area, and the blue lines that you see on the map are not streets or highways. These are transmission lines, right? And the various thickness represent the different voltages of the transmission lines. So in this area is particularly interesting because there are many wind farms. There are 42 different wind farms, and in aggregation they generate over 1 gigawatt of power. And since this power comes from renewables, you know that it's highly volatile, so they can experience oscillations of 20% in the time scale of minutes. So this is a risk for the stability of the grid and for the reliability of the grid, because it can lead to line overloads and damage to the equipment. Right? So what operators do to contrast this, it's brute force curtailing renewable powers. What this means is they just take off renewables from the grid so that they don't cause these overvoltages. And this is a waste, of course, because this is green energy that could be used for better purposes. There are two possible solutions for this. One is what they call physical reinforcement, meaning just building new lines. Now they can accommodate more capacity, so renewable energy is not wasted anymore. But this is very costly, as you can imagine. And the second option is what they call virtual reinforcement, but what we control theorists would call control. Right? So this essentially accounts for using the assets on the grid, so generators, flexible loads, energy storage devices, to stabilize the grid in presence of this renewable generation. Right? What this means in practice is modulating the set point at which these assets operate in order to make sure that the voltages and currents of the line stays within the limits. Right? And this is of course cheaper because there's no major construction project involved. It's just applying a smart control into the way we operate existing assets. Let's take a look at this problem, but from a math point of view. So what this really is a steady state optimization problem of this sort, right? So we're looking for minimizing a cost function phi by choosing judiciously this control inputs U, right? These could be many things, right? So it could be, for example, active power curtailment, set points of the regulators, active and reactive power injections of these assets that operators have on the grid. And the objective could be different things, but usually minimize the curtailment, so we don't want to waste renewable energy, and perhaps we want to track some operational profiles that are given beforehand. This is subject to some constraints, right? So there are actuation limits, so we don't have infinite active and reactive power to use to regulate the grid. And there are also some physical constraints that are those that are more important for us. So we want the voltages and the current on the lines to stay within the limits that guarantee reliability of the grid. So and these are the constraints on the Y. Then I didn't mention this explicitly, but there is of course a connection, direct connection between the control inputs U and the output that we measure in the grid, so the voltages and currents, what you see here on the slide, they're represented by the Y. And this connection is through a nonlinear input-output map, H, right? That represents really the physics of the grid, right? Or in other words, the power flow equation, right? So in other words, voltages and currents on the lines of the network are a nonlinear function of the reactive and active power that we inject. Not only that, but it's also a function of active and reactive power that is injected by some external entity that we don't have control, or operators do not have control on the grid. And we present that by this variable W, right? Which is, from a control point of view, is an exogenous disturbance, right? This could be, for example, uncontrollable loads, variable microgeneration, right? And this is the reason why here at the top of the slide we have this asterisk on top of steady state, because the W varies over time. So this looks like a steady state optimization problem, but it really it's a parametric steady state optimization problem that varies over time. And what operators are interested about is not just regulating the plant, so the transmission grid there, but tracking solution trajectories of this slowly time-varying optimization problem. Okay, let's take a look at what industry do right now. We would paraphrase that as control theorists as offline optimization. So they use forecasts of the disturbance that happen on the grid over the next day. And then they use optimal power flow solvers, right? So we can represent these solvers as an interconnection between a model that we have of the grid, so this hat H, so a power flow model, and some optimization routine that use this model in order to find the optimal injection in the grid, right? And this is done completely within your computer, right? There's no implementation. It's run until convergence. And then the outcome of this routine, it's then deployed on the real system, right? Apologies. It's deployed on the real system. That operates, of course, online. Right, we would call this feed-forward optimization, essentially, in control. There are some problems. It's heavily model-based, right? So we need a model of the grid in order to run this. It could be computationally intensive if you try to solve this problem on the scale of a whole country or a continent. And we know, as control theorists, that feed-forward is not robust to model uncertainty and also to external disturbances. You may have heard of this episode on the Iberian grid in, I believe it was April or May of last year, that led to a major blackout. And actually one of the reasons why that happened is excessive voltage on the grid and inappropriate response by the operators. So this is a very relevant problem at the moment. Okay, a solution that has been proposed in the literature is what we call online feedback optimization. So the main idea is to just get rid of the model of the physical grid and directly connect our optimization routine with the real physical system, right? And this creates a cyber-physical interconnection between an optimization routine and a physical plant. What are the advantages of this approach with respect to what we've seen before? There are a few. So it's computationally light. We don't really need any model of the grid. We just outsource the evaluation of the model at the physics itself. Feedback has a sort of this forgiving nature. So even if you have, let's say, wrong information about measurements or input-output models, then the feedback automatically corrects it. And it's almost model-free. I'll get back to that. These are nice numerical simulation that my former colleague Lucas ran on the part of the transmission grids that I've shown you before, using this approach. And, the interesting bit for you at least to understand from this is that this approach was able to track what is the theoretical optimal curtailment or renewable almost perfectly, and it does that with a high level of complexity, right? So this is how the various operational points of the assets are changed throughout the time of the simulation. And you can see there are many assets that are changed automatically with something that would be extremely hard to do by manually or semi-automatically by an operator. So it's a great thing, but let me dive a little bit deeper into this so you can have a better idea on how these methodologies work, because so far I kept everything very high level. So this is the steady state optimization problem that operators are trying to solve. I've seen it before. For the purposes of keeping this derivation neat, we get rid of the output constraints, and we can use, for example, some soft constraints, right? So instead of enforcing it in a hard way, we can just put an extra cost, an extra term in the cost function that penalizes deviation. And here on the top right of the slide is an example of this. Right? Okay, we're in this simplified setup. The next thing is to just get rid of the y. Right, we see the y, it's a redundant variable. We can just substitute the cost function. Now we're optimizing our u. And then at this point we have an optimization problem that we can probably solve with some routines that we know. Do you want to guess what something that you could run onto this to find a solution? An optimization problem? An optimization algorithm?
Gradient descent.
Yeah. So gradient descent with the projection, because we have constraints on the u. So this is something that we can run. This is how it looks like, right? So the next estimate of the solution of this problem is given by taking a step of length gamma towards the descent direction of the cost function, so the gradient, and then we project everything into the constraints u, right? The expression in the second line essentially shows you how the gradient looks like, because we have a composite objective function, right? And this is how we can work out an expression. So we have a composite cost function with two arguments. So we have to take the derivative, the gradient with respect to the first argument, and then the gradient with respect to the second argument. In order to derive it, we need to apply the chain rule, because it's a composite function, right? So we take the Jacobian of the mapping H, we transpose it, and then we do the multiplication for the gradient with respect to the second argument. Right? Okay. Now, here's the kick. What feedback optimization does, differently from feed-forward, it does not rely on the model, on a model of the grid in order to evaluate the H, but just replace that with measurements that you take from the real grid. Okay, and these are essentially, if you have very good, let's say, timescale separation, it's very close to the actual steady state of the system. There's another bit that I didn't mention explicitly, but it's very important, and it's this gradient of the steady state mapping of the system that people call input-output sensitivity. Right? This is something that is in theory not given a priori, and it's at least in the context of grid, it can be derived, or a good approximation of this can be derived offline just based on the parameter of the grid itself. And the difference is that with respect to having dynamic models is that you don't need to know the dynamic models. You can derive this without knowing the real dynamics of the system, just based on the parameter of the grid, like impedances, resistances, etc. Okay, we have this routine, and then we can write explicitly as this cyber-physical interconnection, right? We take the measurements from the grid, currents and voltages, and then we feed it into the projected gradient iteration, and then what comes out of this iteration we feed back to the grid. There are several conceptually related works to this. The first that comes to mind, it's Extremum seeking, right? The main difference with that is that in Extremum seeking you have more stringent assumption, or less stringent assumption, in the sense that you don't know the gradient, you cannot evaluate the gradient at all. So you need to rely on zero-order information in order to estimate it. Another one is real-time MPC, or real-time iteration. It's still a cyber-physical interconnection between optimization algorithms and physical systems, but you're dealing with MPC, so you're optimizing over transients. Here we're interested about steady-state optimization. And maybe before proceeding, a disclaimer. Here we're not doing a comparison between these methods, not claiming any superiority of anything with respect to anything else. In most cases, advantages and disadvantages are problem dependent on the specific application, right? A good way of thinking about that is that these online feedback optimization methods are a good compromise between extremum seeking and MPC. You need to know a little bit more with respect to extremum seeking to deploy them, but they are computationally lighter than MPC that requires dynamic models of the system and optimizes over transients. Okay, let's get back to this feedback interconnection. This is just an example of application for which online feedback optimization has been proposed. In the context of power grids, there are many. Here I listed just a few. For example, it's been proposed also for dealing with N-1 curative actions, essentially resilient action when one link of the grid fails. Fault var regulation in distribution systems, and it has been also deployed in real microgrids by demonstration projects, and my colleague Lucas also deployed in a real distribution system in the canton of Aargau in Switzerland, and it's currently working and serving 100,000 people, regulating the power grid there. There has been some applications on smart mobility, for example for ramp metering, so regulating the traffic into a ring or city with the goal of decongesting. And for high ride-hailing sampling, essentially how to distribute ride-hailing services to serve demand in a good way. There has been some also applications in robotics for the autonomous driving and coordination of multi-agent autonomous systems. And some applications to industrial processes. And I don't know much about that, but I'm sure Marta, for example, knows way much more. Okay, so applications are a lot and very interesting, but what about theoretical guarantees? Do we have a theoretical understanding of what happens when we interconnect an optimization algorithm with a physical system in this way? So there are various questions that have to be considered. I would say that probably the most popular important one is closed loop stability. We know that when we interconnect two dynamical systems, the interconnection could be stable even if the two pieces taken singularly are stable, right? So we would like to come up with some guarantees that show us that the interconnection remains stable and the optimization / controller does the job that we want it to Tracking performances. We mentioned that we are not really interested about just a regulation to a steady state, but we want to track solution trajectories of this slowly time-varying steady state optimization problem. So we would like to know how good we can track these solution trajectories. What is the tracking algorithm, if there are any guarantees there. And another one that is very fundamental but less investigated is robustness to input-output model mismatch. So the underlying assumption of feedback optimization is that we know the sensitivities, so the input-output behavior of the system. This is not always true in practice, and when there are errors there, you would like to have some guarantees that things will still work well. There's a nice paper from Marcello Trombino that studies that, and I believe not much more after that. But it's an interesting point. Okay, so let's focus on closed-loop stability and tracking performances. I just want to give you an overview of what's out there in the literature regarding these theoretical questions. I would say we can categorize it in two main blocks. The first one works under the assumption of perfect timescale separation. So they assume the plant can be represented by an algebraic map, right? So it gives instantaneously the output at steady state of the plant once we give the input and we know the disturbance. And the algorithm that we're trying to deploy are just iterative algorithm from optimization. Gradient descent was one, but you can think about others like primal dual methods or second order methods like SQP or things that are sort of with game theory like best response playing, etc. So under this let's say framework, there has been many papers and many works that study closed loop stability that in this case maps 101 on convergence analysis of classic optimization, right? Because you're looking at an optimization algorithm just with a nonlinear constraint. So tools for optimization are enough to study stability. And you can extend this in the case of time-varying problems, developing tracking analysis, and you can borrow tools and analysis from time-varying optimization. Okay, the second, let's say, class of analysis relies on the assumption that there is no really time-scale separation. So the plant is a dynamic model, right? This is a nonlinear dynamic model. And they look at optimization routines not as iterative algorithm anymore, but as flows, right? Like gradient flows and in continuous time. And the reason is that analysis is easier because both blocks live in the same domain, and you can build analysis based on the Punov and LaSalle tools to study stability, closed-loop stability, this continuous time interconnection. And you can extend it with input-to-state stability tools when it comes to time-varying problems. Okay, what we are interested about here in this talk, and what I'm going to tell you a little bit more in the remainder of this presentation, is about this approach on line feedback optimization, but targeted to complex multi-agent systems. Right? We're interested about building an analysis that is worth and useful when the systems that we're trying to control are large multi-agents and distributed. And this adds more complexity to the analysis. The reason being that the iterative algorithm that we're trying to deploy, it's really an iterative algorithm. You can think about a very complicated routine that you implement on your computer that calls QP solvers and other, let's say, implicit routines for optimization. So what we have, it's a sample data set, right? Where the plant lives in the continuous time world and your optimization routine lives in the discrete time world. Right? And the analysis that has to be built. So this was one of the challenges that I'm going to talk about. Yeah, there are others, of course. For example, the decentralized or distributed implementation of these approaches. When sensitivity is not known globally, but it has to be reconstructed by local agents. And another important problem for this setting is the tuning of the step sizes, right? So when you have a large scale distributed systems, you want to have adaptive algorithms to tune the hyperparameters of these controllers to make things work well. But I will focus on the first two challenges, so sample data analysis and a modular design framework that perhaps goes beyond optimization. And the reason is that the kind of algorithm that you want to deploy to control your system might vary very much by the system itself, the kind of distribution of the agents or the properties of the problem you want to solve. So you want to build an analysis that is modular, that takes blocks like the optimization block and the system block and gives guarantees based on general design principles of these singular blocks. Okay. Okay, this is the menu for the rest of the talk. I'm going to tell you about this modular framework for the analysis and design of feedback optimization controller that is targeted for complex multi-agent systems. And I'm going to tell you how this builds beyond classic optimization for multi-agent settings. Then, if there is time, hopefully, yes, I'm going to show you some nice experimental validation on Swarm Robotics. Maybe I can take a break here if there are any questions.
So at some point there was this H, capital H matrix that describes the input-output map.
Yep.
Are there cases in which this is a constant matrix rather than being a function of U and Y?
Yes. So if your plant, we're talking about this panel, right?
Yes.
Yes. So if your plant is an LTI system, then it's fair to say that the sensitivity is a constant matrix. If you have a nonlinear plant, that's not true anymore. So what practitioners do is to build approximations of that work well in let's say in numerical examples. The nice thing about this approach is that the feedback is sort of forgiving, so even if you have some mismatch in how you really compute this sensitivity term, then the interconnection remains stable. The feedback sort of accounts a little bit for this model mismatch.
And in the nonlinear case, this approximation is meant to be around the steady state. So
yeah, I guess the operating point that you want the system to be at, yes.
Excuse me,
yes.
Related to that, so in this case, assume you receive the W from the outside. It's based, in this case, the grid, it's based on the predictions.
Yep.
Is that correct? Because you still need W to compute, it's kind of a model, right, for the gradient? I think maybe the previous slide. One of the previous, sorry. Before you call it capital H, yes. It's still, this is a model, it's a sensitivity that you call. So in practice you're getting this from the predictions, or also you're estimating the distances somehow. How does it work?
So it's really problem dependent how you build these input-output maps. In certain applications like power grids, you can have good approximations that are based on the parameters of the grid. Like, you know, the impedances and the reactances of the lines. You can build an approximation which work well in practice. For LTI systems, you can construct it from data, perhaps input-output data. But for them, in general, you don't know it, and so you need to rely on approximations.
Yeah, I'm curious about the specific case of the grid, because you said like these are like the micro producers and against the demand. And I'm not sure if we're measuring that, we're measuring Y, not W. So where are you getting this from?
Yeah. So, so the approximation, in short, the approximation that you built is not based on W on forecasts. It's based just on the parameters of the grid.
Oh.
Okay. when it comes to replacing the, let's say, the yellow blocks there, you don't need to measure W
Yeah.
directly, just measure Y,
Yeah.
the output of the grid.
I'm asking about the red one.
Exactly. So that one you build it without forecasts. You build an approximation of that just based on the parameters of the grid, and you hope that it works.
Okay. Clear, thanks. Yeah.
Yes.
I have a quick question. Do you have a sense, or can you say something about what the impact is on the actuators of the system? You're doing the optimization, and you would assume that the more you know about your actuators, or also the demand side of your system, the more you can take them into account in order to limit how much they are being strained. So I'm coming from a background of wind farms, so these wind turbines resonate with me, and if there's long time scales between the turbines, but the grid is operating at a much higher frequency. So if one turbine does something, the second turbine will feel with the 10-minute delay what the first turbine did. If your optimizers or your online feedback optimization is running at a really high frequency, you down upregulate the wind farm a lot, and the turbines have to do a lot in order to match that high frequency signal instead of having a longer time horizon to maybe have a smoother actuation signal.
Yep.
So that's where I'm coming from.
Yeah, I know. Yes, no, absolutely. So the performances in terms of tracking and stability guarantees depend on the timescale separation between these two blocks. So
Yeah.
you need to modulate it until it works well. And that's why what I mentioned for adaptive tuning of step sizes and perhaps also sampling time of this approach. It's very important to make things work smoothly.
Okay. Yeah.
Okay, so this is a little bit the outline of what we're going to see till the end, and we're going to start from the theoretical bit. So here I'm going to start telling you our framework, what are the main assumptions. So we consider nonlinear continuous time plans of this kind, and we assume that f and g, the function of this nonlinear model, are regular, by Lipschitz continuity exeter, and the sets from which we draw the control and where the disturbance lives are compact. Right? So we have compact control, inputs and disturbances. And the most important one is that we assume that the system is stable, or destabilizes to the steady state whenever we keep the input constant. So we fix the U, and we assume the system is robustly stable to the steady state U, H of U and W. Okay? And the last bit is that it's not only stable, but it's also input to stay stable with respect to the disturbance W. Right? So if we have a variation of the W, our system doesn't blow up. This is what it means. So we can paraphrase all this as we need a stable or pre-stabilized plant. Why pre-stabilized? You could have an unstable system, but you know how to stabilize it. You can close the loop with something that you know stabilizes, and that takes into account just of the stabilization. And then you can run our feedback optimization routine on top for optimality purposes. Okay, let's take a look at the control objective. This is a bit critical in this shape, so I need to break it down for you. So far we have seen about steady state optimization problems. Here we're looking at the generalization of optimization problems, right? And this is a generalized equation with a specific structure, right? This condition here captures optimization. You can think about first order optimality condition of optimization problem. It can be written as finding zeros of gradients, right? So in this case, the mapping G would be a gradient of a cost function, and A may be something that accounts for the constraints like normal cone operators. But this condition can represent more general problems, for example, equilibria in games and other things. So we decided to, for the purpose of building a very general setup, to consider this generalized equation as the control objective rather than mere optimization. But again, this capture optimization as a special case. And the assumption is that the solution of these generalized equations are strongly regular for all possible parameters W. What it means in practice, if you think about optimization, it's you have isolated the local solution of your steady state optimization problem. So as long as we don't have continuum of solutions, so for example we have strongly convex problem or locally strongly convex problems, it's fine. Okay, let's take a look at this, the blue block, so the optimizer, our optimization routines. What are our assumptions of the optimization block? 3. So we assume that the fixed point of this optimization routine, which is written as a general map T, that is function of the previous input U and what we measure for the grid W. The fixed point of these are solutions of our generalized equation. Right? This is just, it's a sensible thing. The algorithm does what it's supposed to do, finding solution. And then we assume the dynamics of this optimization algorithm, right? Because this optimization algorithm can be seen also as a dynamical system, are locally robustly stable. So they converge to local optima in a robust way, right? If we perturb the optimization routine with some W, then it will still converge towards a neighborhood of the solution. It won't blow up. And then some Lipschitz continuity of this general mapping T that describes the optimization algorithm. Just for you to fix the ideas, this T could be the gradient step, right? So the example that you saw before. So we paraphrase this assumption as robust convergence of the algorithm. Excellent. So we described our 2 blocks and the assumptions that we made on these 2 blocks. Now we need to interconnect them, but one lives in the discrete time world, the other in the continuous time. So we need a zero of the holder. And then we need the sampling from the continuous time plan to the discrete time one. So we live in this sample data set. Let me see the time. Okay, we're running a bit short, so I'll be very brief on this part about the analysis. So the way that we build the closed loop stability analysis starts with discretizing the plant. So now we have the 2 blocks living in the same world, discrete time systems. And we look at the problem in error coordinates. Right? So now the state of the upper block is the plant error, so the distance of the steady state from the relative steady state with constant input, and the optimization error, so how much we're distant from the solution of the generalized equation. So let's say we translate the interconnection in error terms. And then I'll be very brief here. The idea is to use the small game theorem. So we use the assumptions of input to state stability of the plant and the algorithm, combine them together using the small game theorem, and we get this condition here, where these 2 parts here are the asymptotic gains of the 2 blocks. And if this is satisfied, then we know that the interconnection is input to state stable with respect to the disturbance. Let me focus briefly on this condition here. So this here is the gain, the asymptotic gain of the system, and is a function of tau, which is our sampling time. So we can modulate this by changing the sampling time. Right? And in particular, this decreases when the sampling time increases. So if this decreases, we have a better chance of having this condition satisfied. Whereas this is the algorithmic gain, right? And it's a function, actually, it's also a function of something that we can control, although here it's not written explicitly. By changing the hyperparameters of the algorithm, we can also change its gain. So in short, by modulating the sampling period of this sample data interconnection, we have a way of guaranteeing closed loop stability of the interconnection, under, of course, these 3 main assumptions. Excellent. A brief check whether to see if these assumptions that we have are strict or not. So we build a very simple example. In this case, the objective is what we would say set point tracking. So we're interested in minimizing the distance of the steady state of the system from a reference. with some input constraints, right? And the system is just dynamical systems governed by the second order differential equation. So it's a second order, it's a two-dimensional state space system. We first verify that closing the loop can indeed lead to instability. So the two blocks taken singularly are stable, but if we interconnect them and we modulate the sampling time in a wrong way, we get oscillations, right? So we need to reduce the sampling time enough, increase the sampling time enough in order to retain stability. And the second one has to do with the assumption that our algorithm is robustly stable. We look at this gradient algorithm in the case, I didn't write it explicitly, okay, but the gradient algorithm in the case we have vanishing step sizes. These are popular in machine learning context because they guarantee stability with very weak assumptions on the cost. But this doesn't work in online context. You can't use these things for control. And the reason is that your controller / optimizer loses aggressiveness, loses grip until the point at which you can't track anymore the solution trajectory. Okay, excellent. So we built this very powerful analysis. Let's take a look at how we validate it. And we start by a problem in multi-agent autonomous systems. In particular, we look at this optimal coverage problem. Right? We have a set of drones that we want to deploy on a working area in an optimal way. And optimality is defined by this optimization problem here. Right? So it's a summation over this contribution that are drone specific. And this contribution essentially says what is the cost of a single agent here to take care of this Voronoi Tesla here. We have, of course, some limitation on the input U, which is the reference position that we give to a single drone. Okay, the steady state object is the optimal deployment, and this condition is the steady state condition, right? So we give reference position to the drones, and then the local controller of the drones will take care of bringing the drones to that specific position, right? So at steady state, this is just an identity. And here's the kick. This is not the steady state optimization problem, this is time varying, right? Because the distribution here on the working area that we would like the agents to track optimally can varies over time, and so the drones need to follow this optimal coverage trajectory that changes over time. So I had a very talented student who deployed an online feedback optimization controller on this experimental setup. We use these very small drones called Crazyflies. They weigh 27 grams. They're 9 centimeters wide, very, very small. And we had these cameras here that take measurements of the angle and position of the drones. The communication and perception of the drones is simulated because the drones don't have cameras, they're too small, but we simulated it in the implementation. And the computations are actually on board of the drones, in these small chips here. Okay, there's a very popular algorithm called Lloyd iteration that solves the problem in the case of, let's say, time invariant case of the problem. But we want to do this online, right? So, again, the drones are pre-stabilized by local FPC. And the density function that we're trying to track is time variant, right? Okay. Let me skip this one. I'll give you this directly. So this is just a representation of how the drones now, just by virtue of local communications, track the optimal deployment. And here, of course, this is built in post-production, so to speak, and shows that we're tracking this optimal deployment that changes over time, despite this density function that defines the optimal deployment also changes over time. Right? So essentially, our assumptions are satisfied, and the system does what it's supposed to do. So it tracks the optimal trajectories with bounded errors. Okay, so there are other applications that perhaps are more relevant. We wrote a few papers on application of complex multi-agent systems. One, it's a tutorial on multi-area transmission grids. So we've seen at the beginning of this presentation that online feedback optimization can be deployed for controlling transmission grids, but different countries have different grids that are interconnected and they are controlled locally. So we want to understand what happens when these local controllers interact among each other by the physics. And this framework that we built takes into account this case. And there's an interesting game theoretic interpretation of these situations. And I suggest if you're interested about the topic to read this paper. If you switch things around, let's say the theoretical framework still says something interesting, right? So if now you don't have physical systems anymore, but social systems where the local agents are users of social networks that they exchange opinions all the time, we can look at recommender systems as this dynamic feedback controllers using the framework that we developed. We can try to control opinion distribution in a social network in this way. Okay, and I want to conclude with this slide just to give you an overview of all the challenges that happens in feedback optimization for complex multi-agent systems. I'll stop here and I'm happy to take questions.
Any question?
Please.
It was nice talk.
Thank you.
So if you go to the previous slide, so the thing that we know is that from online feedback optimization, one of the main assumptions is that the system is like locally stable, the dynamics is exponentially stable or locally stable. But now if I consider, let's say I'm applying OA4 at this multiple stable systems which are interconnected, then I feel that it somehow becomes some sort of a dynamic game, because there exists some common states which depends on the coupling decisions of these small systems. And as far as I know that for dynamic games, there doesn't exist much theory for the stability of this whole dynamics. So do you have any idea how we will tackle, or as we start to look at this problem?
Let's say, from the perspective of a sub-transmission grid, what comes from the exterior, so from the other grids, can be seen as a disturbance, as an exogenous disturbance. So I guess if your analysis or assumption is that your local part of the grid it's stable with respect to input to stay stable with respect to external disturbances.
But that's a strong assumption, right?
I guess it's a strong assumption, but you can, let's say, pre-stabilize local bits of the grid, right? That's what they do with loop control, for example,
I see.
or other methods.
Thanks.
Yes, please.
Thanks for the nice talk. My question was that, as far as I understand, you treat the output constraints as a soft constraint by putting them into the post function. I wonder, did you ever consider the cases where they have to be a hard constraints and you have to exactly, explicitly ensure that they hold?
Yeah, that's a great question. Let me find the right slide to answer this. So what I showed before, it was just an example to make the, let's say, the analytical derivation intuitive. But in this general theoretical framework, we can absolutely deal with hard constraints. Right? So I didn't say anything nor exemplify the sort of optimization problems that this generalized equation captures, nor the algorithms, but it's very general. So here you can have R constraint problems as special cases of this generalized equation. And you can have algorithms here that can solve this R constraint problem. Also second order methods like SQP or Newton steps.
In that case, as far as I understand, some of these theoretical results do not necessarily hold. Is that correct?
No, so the analysis that we built covers these cases.
Okay.
So you have theoretical guarantees for problems with hard constraints and algorithms that solve hard constraint problems on the output.
Thank you.
Yes, ma'am.
So to kind of follow up to that, how can you have strict output constraint satisfaction without knowing the mapping exactly?
Asymptotic constraint satisfaction.
What do you mean by asymptotic constraint satisfaction?
So, I mean, it's not MPC, right, where you satisfy at all times the state constraints or the output constraints.
You can violate constraints if you don't know the mapping, right?
Yes, you can very well violate them online, but asymptotically you converge to a feasible solution. Yeah, it's hard. If you don't know the dynamics,
Yeah.
it's hard to satisfy constraints on the state of the output online. I mean, MPC does so, control barrier functions maybe, but they're all methods that rely on knowing the dynamics of the system.
Yeah,
So if you
everything
don't,
depends on the model, right?
But yeah, it's a good point.
I'm curious about your observation that diminishing step sizes break the whole loop.
Yep.
Does that mean that when you have diminishing step sizes, your small gain is actually not finite, or you don't have like an input to state stable algorithm? Is that the case?
Yes. So again, this has to do with the assumption that we have that your algorithm is robustly stable.
Yeah.
Right. So, and this is not the case if you have vanishing step sizes, right? Because in that case, let's say the aggressiveness of your algorithm vanishing asymptotically over time. So, if you have a disturbance within the algorithm, this W can blow up the whole thing. So you don't track solution trajectories.
Thanks.
Yes.
So in the multi-area case, where we have multiple of those loops between physical system and discrete time algorithm, potentially, would you think we could apply the small game theorem separately so that we allow for different sampling times all over the different sub-areas?
I don't know, I don't feel comfortable in guessing. One may try. I don't know what comes out of that, to be honest. I mean, the analysis should be made from a centralized point of view, at least the way that we constructed that. So the algorithm, the game theoretic algorithm needs to be robustly stable, and the interconnected system needs to be robustly stable already.
I'm thinking of an overall gain that depends on the individual local gains, and as long as the total one is less than 1, then the local ones might have different sampling times.
Yeah, I guess one could try to build such an analysis. It would be probably useful for distributed systems.
All right.
Thank you. Yes.
Can you talk a little bit about scalability? What's the scale of the systems that you can apply your method?
I mean, it's computationally quite light because you're not, for example, if you contrast it to MPC, where you solve an optimization problem over a long horizon to the solution, here you just apply one iteration of an optimization routine. So you can get very high dimensional. In terms of dimensionality, for example, here this is work of Lucas Ortman. I think this problem here, where it was trying to control these local areas of transmission grid, is quite high dimensional, talking about tens of thousands of decision variables. But I mean, in practice, if you apply, for example, projected gradient descent, it's a matrix gradient evaluation, matrix multiplication, and the projection is a QP. And nowadays you can solve it in milliseconds, also when you have large problems.
Yeah, I have a question about the example that you showed in which if you don't choose correctly the sample time, you can destabilize the systems, right? How tight are those bound? Like fairly close, or they are?
That's a good point. Let me grab the right slide. Which one is it? Tell me if you see it.
Yeah, 41.
Yeah, so the bounds that we derive are conservative. I mean, it's sort of expected since the framework is very general. We have all possible convergent algorithms and all possible stabilized nonlinear plans. So we have this example actually comes from the paper. And if you see that, we see explicitly the contrast between the bound that we get from the theory and the empirical bound.
Okay.
In that case, it's fairly close.
Okay.
But this is a very toy example. My conjecture is that if you get to real examples, then the bounds are
Becomes more conservative.
very conservative. Okay. I would say the value of this analysis, more than giving precise bounds, and to tell you what are the general ingredients in terms of plans and algorithms to build a functioning controller. And then it's up to you of tuning things to make them work well and smoothly.
And also, still in this slide, the vanishing step size problem happens also in the case in which you do not have disturbance, or in that case you could actually use.
Probably, if you don't have disturbance, you converge asymptotically to a solution.
Also, okay.
But in the real world,
No, yeah, of course.
Right.
But any other question? No. So let's thank the speaker once again.